Hello everybody, my name is Fraser King and I'm a PhD student from the University of Waterloo studying Arctic snow. Today we're going to talk about some of my work using CloudSat snow accumulation estimates to constrain gridded snow water equivalent products throughout the Arctic. So as we all know, measuring Arctic snow is an important task. It has implications to things like the global water and energy budget, cold region flooding, and water resource management practices. However, as you can see from this image here, there's only a handful of stations that exist in this high Arctic region, and actually only about 1% of these exist above 70 north in Canada. One way to try to fill these observational gaps is to use reanalysis or model estimates. However, there are often errors and biases associated with their estimates of snow throughout this region due to the poorly constrained nature of it. And so I'm here today to talk about another option, which is to use remote sensing instruments on satellites like CloudSat. In this instance, we're going to be talking about the cloud profiling radar instrument on board. So the CloudSat CPR, as it's orbiting the Earth and it encounters an area of cloud cover, it creates a vertical radar reflectivity profile, as you can see here, of the cloud's inner structure. And from this, we can use some optimal estimation techniques to derive interior snowfall rates, and then extrapolating that down to the surface provides us with a surface snowfall rate, as you can see in this bottom panel. This is all packaged into a product known as the 2C Snow Profile, which is what I'll use throughout the remainder of this presentation. And the first thing we want to look at is monthly changes in SWE. So we've got these two new quantities that we're considering. On the left, we've got delta SWE from the blended 4 product, which is, as its name implies, a blend of 4 other snow on ground products. And this is simply the difference in average SWE on ground between 2 consecutive months to get an idea of how this SWE amount is changing. And the corresponding quantity that we compare with CloudSat is the average SWE over that period. So over the same 2 months, we just calculate the average amount of snow accumulation occurring. And then we basically compare these two quantities to see how well they align. One thing to note is that CloudSat can only see accumulation. Meanwhile, the delta SWE value gives information on both accumulation and melt. And so it's important to note that we've restricted our analysis to strictly frozen months where the daily max temperatures are strictly less than 0 for the entire month to really focus in on these accumulation periods. So we're comparing like with like here. And so what we're seeing here is the seasonal correlation comparisons over SON-DJF between the delta SWE B and the average CloudSat accumulation between the beginning of 2007 to the end of 2015, so approximately 107 delta periods. And what we find is generally a very positive overall correlation, which is quite good. And you can see from the spatial distribution on the left what that looks like, as well as the distribution of what those individual grid cells, the correlations look like in the histogram on the right, with the vast majority being positive, many being above 0.5, and only a handful of these being below 0. Generally, the low correlations and the negative correlations are a result of a small CloudSat sample and issues with CloudSat estimates. And so now that we've got these two quantities, we can compare them and try to identify outliers. So what we've done here is a case study at Resolute Bay, which is a small hamlet located in the Canadian Arctic archipelago. I'm showing on the scatter plot here a comparison between delta SWE C and so CloudSat on the X and the blended delta values on the Y-axis. We've just run a simple linear regression between the two to get an idea of what the relationship looks like, and then generated a 95% prediction interval from that estimate to identify where we would expect from month to month the accumulation values to lie. And then by looking outside of this prediction interval, we can see periods that are sort of statistically inconsistent with what we would expect to see. And I've highlighted one of these cases in red here, where we see a negative delta value from blended and a positive accumulation from CloudSat. So this kind of stood out to us as an interesting case. And this occurred during December to January 2007, 2008. So this is a very cold period. So very interesting that we're seeing this melt event occurring in the gridded product when the period is so cold. And so one nice thing about doing a comparison at Resolute Bay is we can actually compare with in situ data because we have that there. And it wasn't an atypical month. It wasn't warmer than usual. As you can see from the statistics here, it was very cold. And so it didn't look like there was something physical happening that would cause this. And so when we look at the component breakdown of the blended product, as you can see here on this graph with each of the 4 colors representing a different gridded product, we can identify a single product as the culprit for causing this meltdown event that we've identified here. And that is in blue, which is globe snow in this case. And I've marked these meltdown events, the starts of them, with these dashed lines here. What we typically would expect to see is the slow accumulation of snow, but there's something very odd happening in globe snow, which is then affecting the black line, which is the blended 4 daily SWE on ground estimates over this period. And we were able to actually trace this this issue in globe snow back through its assimilated data to the station data at Resolute Bay, which was assimilated. And there was a measurement error that had occurred actually at that site at that day, which had caused a large drop-off in snow on ground and was likely assimilated here by globe snow. And so this just goes to show that this technique can sort of trace back through the different products to find an individual issue that happened at the station during that day in the final product. And so if we generalize this technique from that one station to the wider grid that I had spoken about earlier, we get these results here, these temporal and spatial breakdowns. On the left, we can see the number of outliers by month on the top in red, and then by year in the blue on the bottom. Generally, we see the strongest number of outliers during the high accumulation period between October and sort of the end of January, when there's a lot of snow falling, obviously, throughout the Arctic. Things have cooled down there. And then by year, we see a pretty consistent number of outliers for the most part, excluding years 2009, 2011, and 2012, as these were periods where there were prolonged battery failures from CloudSat, so likely resulting in a lower count there, but otherwise fairly consistent throughout this time. And then on the right, if I move my camera over, we can see the spatial breakdown for each of the different products, the CMC product A, Crocus B, Globe Snow C, and Mara 2D. In general, we get a sort of relatively consistent pattern in spatial structure across the region from all the components, with the majority of outliers occurring throughout the central Arctic archipelago, in parts of central Eurasia where we have very few in situ measurements, and these are regions that are known to be poorly constrained in gridded products just because there's nothing really to assimilate and bring the model estimates back in line with what we're seeing in reality. And so one of the applications we're thinking about here is to do an adjusted blended 4 product, where if we actually mask out the regions that we've identified as being statistically inconsistent using the technique described here in each of the component products, and then recalculating the blended product as an ensemble average between the remaining data sets, we get a new adjusted product. And when we take the difference between that adjusted product and the blended product, we can see the strong negative bias that occurs between the two, which is suggesting that, as you can see here, over the northern hemisphere domain that we've got here, excess accumulation in the original blended 4 product as a result of the outliers, suggesting that, again, there's a large amount of accumulation happening that could be classified as an outlier or statistically inconsistent with what we would expect to see from year to year. And so this leads into this data quality flag that we're generating for these statistically inconsistent periods. As you can see on the left here is an example from Mara 2 that are generated by us providing these gridded products. In this case, we've been examining the blended 4 and its components, as well as the CloudSat CPR 2C snowfall product. Taking these new quantities, comparing them, using some pre-processing where we only examined frozen months, as well as samples with a large enough CloudSat sample size. And then using this prediction interval, we're able to identify periods that are sort of inconsistent with what we would expect from year to year. And so in summary, can we use CloudSat to enhance current gridded snow products, right? This was our overarching question. Well, using this technique that we've discussed in our previous works, where we're aggregating CloudSat estimates over high latitudes and the strong performance we see there, as well as the accumulation period agreement that we're seeing throughout the region that we're comparing here, we can use this outlier detection technique to identify statistically inconsistent periods, like the case we saw at Resolute Bay, to trace those back and find out why we might be having issues in the gridded products that we're looking at. And then this can lead to applications like the quality flag that we've developed, as well as recalibrating things like blended products to identify if there might be biases that exist because of these statistically inconsistent periods that we're outlining. And all of this is done automatically using the process we've developed with CloudSat CPR estimates. So this could be applied to any other gridded product that you might be interested in that has snow on ground estimates. And so that's all I have for you today. I'd just like to thank you for watching, and I would be open for any questions that you might have for me now.